Okay, this is for an infinite line charge. You got a point P, X naught, Y naught. Um, you have the R vector here. And we have its components. We did this last time. But yeah, if this sample point is X star, then from here to here is X naught minus X star. From here to here is Y naught. So the vector from here to here is X naught minus X star times I plus Y naught J. Okay. We'll make a change in my notation here. Okay, now this is the point X naught, Y naught. Well, just make note of this distance is A equals, well, it's just Y naught equals A. And we won't use that A until we get down here. I'll keep the X naught, Y naught notation throughout. Seems like never to write it down anymore. Okay, so very simple. Your delta L vector is a delta X times your I vector. In other words, delta L is in this direction. Your current is in this direction. So I delta L is positive. M equal to I times delta Xi right there, crossed with your R vector. And I left my K prime off of this. Also note K prime is mu naught over 4 pi. Just as with the electric field permittivity and so forth. Okay. You have the permittivity is 4 pi K. Sorry. Yeah. Okay. Anyway, we have this. Okay. Now, do that cross product, you get this. So you integrate this. And you integrate this and you end up with this. And you do the integral, start with the trig substitution. Okay. Get this, which could also be written mu naught I over 2 pi Y naught squared, not this not squared, 2 pi Y naught. And mu naught I over 2 pi A, where A is Y naught. So right there is the field due to the infinite line charge. Okay. At distance A from the charge. Now, let's say now you've got an infinite sheet of charge. Now your text puts this infinite sheet, put this infinite sheet. Now your text has it oriented in the y direction, something like that. Your text has a better picture of it. They got this infinite sheet of identical line charges. Pick your distance A above the sheet. then whichever wire you're above, going to produce this field. If you look and on some these are the ends of the wires or whatever it is current the line charge. If the field is into the bore, then I is this way, and your right hand will tell you that your field surrounds each of these line charges. Well, much of arrows in counterclockwise direction. Now, if we go to distance A above the line, so that this distance is A. Let's look at the field from usually shows up pretty well. Okay. Now, if we look at the field just from this charge, it's going to surround the charge. Kind of like this, the field is going to go this way. And here, the field is going to be to the right and down. I'm sorry. Yeah. Okay. That's right. Okay, now we take another charge on this side equals to -2. Then the field is going to surround it like so. So what you're going to end up with is a field like this. Okay. The resultant is going to be that's the field from these two. Now that's not a very big field compared to the field you get from, let's say, this charge, because this charge is a good bit closer than this. So if this charge is twice as close as this, it's not quite twice as close, but it's going to produce a field. At this distance, which is going to be bigger in magnitude than the field you get from this one. And it's also going to be in the counterclockwise direction, so that this charge would produce maybe this much field. Now, if you take a charge over here, it's much further from your field point. Say it's 10 times as far. Okay. Being 10 times as far, the magnitude of the vectors that surround this point along a curved big circle like this, going to be two things. It's going to be 1/10 this rate, So your arrows are gonna be 1/10 as long. And by the time the circle gets around here, it's almost vertically down. So the component of the field you get from a wire way over here is going to be 10 times smaller and nearly vertical down. So it's probably going to be about 50 times less than this green arrow. Well, actually, then this horizontal component of that field will be about 50 times less than the horizontal component in this blue arrow. You have another point at an equal distance over there, another wire, let's say. Then, of course, it's going to produce a field along a big circle here, and it's going to be equally weak, and it's going to be in this direction. It's going to have a component in the x direction. This is about 1/50th of what you get. So you're going to get a vector contribution about here that's 1/50th of the length of this vector. Okay. So from that, you can integrate these, where A, though, is replaced by not only the distance from here to there, whatever the increment is, but also by the sine of the angle that the circle makes with vertical. Okay. Now, that gets a little bit complicated, but you can set up that integral, and don't think you're asked actually to set up the integral, because there's another way to get this. But that's what you could be looking at. And you know, that kind of relates to your multivariable calculus too. You could also take any area income, okay, anywhere on the whole infinite sheet, and find the magnetic field due to the current in that area. And you can do an area. You know, that's outside the scope of this course. Actually, yeah, first year calculus often do get you to some double. Okay. I'm not sure whether that's official and the BCC is, I probably should check that out. But since everybody's doing multivariable calculus, I can talk about that. Okay. So that kind of explains what we saw when we hooked two leads from a 6-volt battery onto this aluminum sheet. And then we put a compass over the top of the sheet. Now, if the orientation was like this, and north was this direction, you find that this, well, that's it. So you got it like so, and north is in this direction. The field of this sheet, if the current's in this direction, okay, current's in this direction, so each wire produces a magnetic field around in this direction, and the compass would deflect from this direction. Got my over toward this direction. Let's do that with my left hand in this direction toward this direction. Okay. Again, let's say this loop is in the X and Z plane. So the y-axis is on top of the axis. Steps to loop like that. Can't really draw that very well, but I can. Okay, so we've got this loop. We got a magnetic, we have a current in the Y direction. Okay. DL, can you recognize that as an L? Recognize D, you recognize that as a D. Okay, use the script just because it's easy, right? Okay. Your DL is just your distance increment or your displacement increment around the loop. Okay. If you integrate the magnetic field dot DL, well, let's just think about it. Let's just say that we have a current I along the y-axis. Okay. Well, first of all, this interval depends only on the current flux through the loop. Okay. Now, if the current is symmetric with respect to the y-axis, then by the symmetry of the situation, you conclude that you have a constant magnetic field around the loop. Okay. If it's not symmetric, like let's say the current goes through this point on the z-axis and still in the y direction, but up here, you're going to get a bigger magnetic field here than you're going to get down here. Okay. Okay, so that the interval of B dot DL B is constant. Now just say symmetric current, but what I mean by that is a current that's symmetric with respect to the y-axis. Then this is equal to 2 pi A times B, which means that it's as if all the current within this loop was just a line current along the y-axis. And if you've got a line current along the y-axis, then at distance A, we know what the magnetic field is. Okay. The mu naught over 2 pi A times I. I is the total current you have through this loop. And of course, that's multiplied by 2 pi A. So it turns out it's just equal to D naught times I total for pi K prime times phi total. Okay. Now, why is that useful? Well, one of the situations that comes up in the problem steps is you have cylindrical duct. Then you have your axis. Of the cylinder. And you want to find the magnetic field at this point, which is at distance of A from the axis. How can you figure that out? Well, first of all, you got a current. I can use R, or I can use A. Not sure what to use for the radius of this big cylinder. So I'm going to use big R. I'll probably regret it. Okay, but there's big R. Well, the current is I. Uniformly. Maybe get over cross that. All right. Can you ponder a minute? Can you use Ampere's law to determine the magnetic field at this point? I'm going to call this P. That's a fancy P. Point K at distance A. Okay, so this picture. We know that the current around any loop depends on the flux through the loop. The flux is the integral of B dot distance increment around the loop. Okay. It depends only on the current flux through the loop. Now, a couple of things about current flux. If your current's in this direction, then you probably want your loop to be in the plane perpendicular to the current. Doesn't have to be. If you want to put the loop oriented like this, then you're just going to have to multiply by the cosine of the angle of this normal vector with this. Okay. And that's pretty straightforward. Now, you want B to be constant if possible, so that you can apply this simple relationship, which is just comes down to this. If the total integral is this, and it's just equal to two pi a times b. Because if b is uniform on a path of length two pi a, which is one loop of a circle of radius a, then this has to equal this. And if you know A, then you figure this out, it's very easy to find B. So it comes down to all we have to do is figure out where the loop is and then figure out what total current flows through the loop in a case where the current is symmetric. Now, I wasn't specific about symmetry, but we'll get to that in a second. Okay, so we're going to draw the loop. It has to go through the point P because that's where we want to find the field. The point P is a distance A from the axis. We want symmetry, and we really should sketch our loop. Not quite hit the point. Get the idea. Okay, points on the loop. Okay. Now, how much current passes through this loop? Okay, so I define here. I total here is the total current through the loop, or the total component of the current through the loop, perpendicular to the loop. Okay, so we have this integral of B dot dl by for B being constant, which implies a symmetric current, or for symmetric current, which implies B is constant. And in this context, we made current symmetric about the axis, like the y-axis, or the axis of this conductor. If B is constant, then you just multiply B by the circumference and you get the integral around the loop. So that integral turns out to have to be mu naught times I total because the field of a current I within the loop is mu naught I over 2 pi a. Multiply that by the 2 pi a circumference, you get mu naught I. Okay, so we locate the loop symmetric with the axis through the point P, which means the loop's going to have radius A, little a. And all we got to do now to find out what the magnetic field is, since in this case, E naught I total equals 2 pi a times your magnetic field. All we have to do is find I total. What's I total? Well, did a good job with that. Good intuition of proportionality. Took about 30 seconds to think it through. That is very good. It's going to be in proportion to I naught, same proportion to I naught as the area of this loop to the total area, because we have uniform cross section, uniformly distributed current over the cross section. In other words, the current density here is constant. And it follows then that I total is this times this. So now, what's B? Okay, got a very good answer on that one quickly. Okay, first of all, I total is this. Loop circumference is A. The integral down. circumference A. B dot DL is two pi A times B, because two pi A is loop diameter. B is always symmetric about the origin, surrounds around the y-axis, surrounds the y-axis or the axis of the cylinder, tangent to the circle. Okay. Get this. All kinds of ways to do this. That's pretty much it. Wait a minute. Yep. So that your magnetic field, as you move on from the center, increases linearly with your distance from the center. Why is that? It's because the effect of your magnetic field falls off with the square of your distance from the center. Okay. But the area of this thing, that's forget that statement. This area grows as a square of A. Okay. The field falls off linearly with A. So if you grow with the square of A, but at the same time fall off proportional to A, that leaves you something that's proportional to A. Okay, does that make sense? I'll write it down. Okay. Pause this for a second. Now, I made a couple of corrections here, like mu naught belongs in here. And just to be sure we got the mu naught, this is equal to mu naught I total. Maybe mu naught I total is this, and this is I total, and this is mu naught. So this follows. Now, I was talking about proportionality. For an infinite line chart, this word is infinite. Okay, and I'm sorry, I keep lapsing into person. For an infinite line current, we just saw that the current, that the magnetic field is mu naught I over 2 pi A. I'll say that the field is proportional to A. You know, proportionality is just mu naught over 2 pi. Okay. And times field is proportional to A. One over, and mu naught over 2 pi A. There's your proportionality. It has to be proportional to A, and of course it is. Okay, because everything else here is a constant, depends on the diameter of your big conductor. Down. Its radius down, so, okay, and the total current. Okay. So we have that. Now, a couple comments again on U naught. I'm not sure that what I wrote here, U naught is 4 pi K prime. I'm pretty sure that's right, but I don't want to think that through. Okay. And I'm not going to just look it up. I'm just going to say that K prime and U naught are both useful. K prime is just a neater expression to use if you're doing the force of a magnetic field on a moving charge. It's K prime Q B plus B. Okay. Or K prime I delta L cross B. And you don't have to carry a 4 pi around with you. If you're talking about the flux, then the flux through a sphere, well, the area of a sphere is 4 pi r squared, or 4 pi a squared, depending what you use for the radius of the sphere. So the 4 pi arises naturally when you're talking about flux. So kind of intuitively, I went with flux here because we're talking about flux. And you could use these things interchangeably, and you really know, it's good to know what the relationship is between mu naught and K prime. This expression we get here is much simpler with mu naught. Okay, K prime QV cross B is simpler than 4 pi mu naught or mu naught over 4 pi. Okay, times QV cross B. All right. Okay, well, there was other things I wanted to talk about. One quick thing is we looked at what happens when we run a current through this thing, these loops, and have a compass over here. It'll deflect the compass significantly at this distance. The current that we get through here with a 6 amp or 6 volt source with its internal resistance and so forth is enough to heat this up to where you don't want to hold it very long. Won't burn you, but it's going to get really uncomfortable after a few seconds. Okay, so I'm saying it probably gets up to 150 degrees Fahrenheit. Maybe not even that. Not comfortable, maybe it's 130. Okay. The field that we get, if we have a bunch of coils distributed along the line. I'll just do this quickly because once you have a picture of Ampere's law, this is actually pretty simple. It takes some digestion. And well, we draw a loop like this, where it cuts some number of coils, okay, over some distance L. So here's the distance we call L. Now this is not, you read what the notation is because this is usually done in terms of number of coils per unit. Like, can you multiply that by the unit length? No, I'm just gonna say, if it cuts N coils over distance L, and we got a current I, Then top of the loop cuts the plane of, or the top of a coil cuts the plane of the loop. And you have current I passing through the loop. Current I passes through the loop once for each coil. Does that make sense? Well, I total is N times L. So in this case, you cut it 4 times. So you got 4 times I cutting this loop. The total contribution to the line interval of the vertical sides comes out to 0, assuming that this loop, or that this loop here is far from the ends. Okay? Why? Because if this loop is far from the ends, you get the same field going up as you have going down. And since you're going in opposite directions between up and down, it cancels out. Okay, so the contribution to the line interval here going this way is equal and opposite to the contribution here going this way, assuming you're not too close to the ends. Make sure we understand that. So that the only place the integral of B dot dl is non-zero is here as we go through the loop and up here. And up here can be as far away as we like it. So that this one can be reduced to negligible. So that I don't have time or room to write out all of this. So I'm kind of saying if you want to read it, okay? Easy to argue that only contribution isn't negligible doesn't cancel. This is part through solenoid. And this thing is what we call a solenoid. Well, it then follows that the integral of B dot dl is just the magnetic field times its length. Equals V times L, but it also equals mu naught times I total. So your field is mu naught over I total, or mu naught times I total divided by L, which equals U naught times NL over L times I. It's I total is N times I, not N times L. And there is another notation that you'll see in most textbooks is a little different. A lot of times N is used for the number of coils per unit length. Okay. And here I'm just using N as the number of coils that are cut, but this gives you a pretty simple argument for the field of a solenoid. That's a big deal. Okay. Okay, sorry for keeping you over.